Welcome back to SanfordFlipMath. This is AP Calculus. We're doing the second day on section 3.1, which is about derivatives. The first half was about the definition of derivative, and this is just a little reminder of where we left off. We were talking about derivative as slope at a point. We were looking at the points on this graph, and that graph should look pretty darn familiar. And what we're going to do today, we're going to extend it in two directions. One, we're going to actually do some graphing of the derivative on top of the graph of the function. Maybe do a little bit of that backwards, and that can be very fun, and by fun I mean completely not fun. And as well as doing some approximations or estimation of derivative based on a table of values. So let's get at it. Our goal, what we have right now, is a graph of y equals f of x. Our goal is to graph y equals f prime of x. In other words, the derivative. Now remember, derivative just means slope at a point. Well, here's going to be the issue. I want to do the slope at a point for all of those points. Not just one of them, but all of them. Okay, so that's going to be a lot of fun, right? Slope at a point. Okay, so here we go. We're just going to start. And this one is actually fairly straightforward, and one of the nice things about this is, notice this. This is really three sections of graph. And what's really cool about these is once you're on these sections, they're all linear, which means the slope is actually the same for the entire segment. So in other words, when I look at these x values from -2 to -1, all of their slopes are the same. Remember again, derivative is slope. So for every point between -2, between x equals -2 and x equals -1, for all of those x values, those slopes will be the same. Okay? Now, my only concern here is that I want you to be able to see the graph of the slopes. So I'm probably going to get rid of those colors for right now. Okay? All right, so this little green section, this thing that was just green, okay, one of the things to note here is the slope is just 1, 2, 3, 4. That's a rise of 4 and a run of 1. And so the slope for this entire section is 4 over 1. Okay? Well, so what I'm going to do is on 1, 2, 3, 4, I'm going to graph those slopes. The numbers that are those slopes are up here now. Okay, now the question is, what about at this point itself? At -2, -1, what is the slope at that point? Well, at this point, the slope to the right of it is 4. The slope to the left of it doesn't exist. And so since it's the endpoint of that function, I can actually just include that for this point, -2, -1, the slope is, you guessed it, 4. Okay, which leads us then to the next question. What about the slope at -1, 3? So what's f prime of -1? I know f of -1 is 3. That's not what I'm asking. I'm asking what's the actual slope at that point? Well, the slope at that point, at this point right here, well, the left-hand slope, the left-hand derivative, as h approaches 0 from the left, the left-hand derivative for this thing is 4. So the slope over here is 4. The right-hand derivative, well, this slope is down 1 over 1. That's -1. So what's the slope at -1 itself? It doesn't exist. All right, so let's back up a little bit then. Okay, remember you can pause, you can rewind all you want. So at the x value -1, f prime doesn't exist. It's not there. So for the derivative graph, I have to have an open circle there. Okay? Now, I'm just a little concerned that that's hard to see, so I'm going to redraw it. But here it is, closed circle, open circle, connect them. Okay? I'm not convinced that that's easier to see, but it's the best I can do right now. Okay. All right, next up. I don't know if it was originally red or blue. It doesn't matter to me. So this guy has a slope for its entirety of -1, because it's going down 1 and over 1, down 1 and over 1, down 1 and over 1. Okay, so for that whole section of graph, I'm going to go to -1 on my graph from this x value to this x value, okay, so from -1 all the way to 3, those slopes were all -1, and remember, I'm doing a graph of slopes. Okay, so this is what I'm trying to graph, is slopes. Okay, so again, the slopes from -2 to -1, those slopes were 4. The slopes from -1 to 2, those slopes were -1. Okay, so the slopes of the original graph were that number, so now I'm making a new graph of its slopes. Okay, this is a lot of fun, I know. This last little guy right here, it has a slope of +1. Okay, so what I'm going to graph is positive. Ooh, that was fun. What I'm going to graph is +1, and I'm going to graph it from x value 2 to x value 3. Okay, so now, again, endpoints can be included in this, but the points in between, again, here's a slope of -1, here's a slope of +1, so at the x value 2 itself, which do you pick? Well, you can't pick, so that derivative doesn't exist. All right, so I just wanted to get rid of that. Let me fix my graph. Okay, open circle here. Okay, again, up at the y value 1. This one can be closed. This one's open on the left. Okay, and that's it. Okay, now I'm going to leave it at that. You can rewind and listen to me say the same things over and over again all day long. So just feel free to do that. Okay, instead of me just repeating here. All right, this is going to be a lot of fun. And again, by a lot of fun, I mean not. This is a graph already of y equals f prime. Okay, so this is the original graph. What my goal is to graph the function that this derivative came from. Okay, so this is the original graph. This original graph, excuse me, is the graph of derivative, or the graph of slopes. Okay, I need to take just a little bit of an aside. Okay, let me carve out the corner here. And if I had a line that had a slope of 2, let's say, because the graph that I'm giving you on this page has a lot of different slopes on it. Okay, if I just said draw a line with a slope 2, well, you could start out at 0, 0, go up 2, and over 1, and you could draw a line. And that would be the graph of a line with slope 2. You could also start out at -3 on the y-axis, and you could still count up 2 and over 1, and you could draw a line with slope 2. The fact is without knowing where to start, there are many, many graphs you could draw, but the difference is that they would all be parallel. Okay? All right, so keep that in mind as we start this. Now, here's the issue. I'm just going to pick a spot to start. I don't really know where to start this graph, so I'm just going to pick a spot. I'm also going to start out with one of the corners of the graph because that's where things, kind of change and stuff like that. So I'm going to start at this x value. Okay, and I'm going to go ahead and start on the y-axis. And again, this is a very arbitrary choice. I'm just picking this spot because I just want to pick somewhere, right? Okay, so if this is a graph of the slopes, if this whole thing, so this would mean the slope was 3. Its y value is the slope of the graph I'm going to draw. This point would mean that the slope was -1 for that x value. This would mean the slope was 1 for that x value. This would mean the slope was 0 for that x value. Okay? Remember that this is a graph of slopes. The y values on this graph are slopes. On the graph that you start with, they're slopes. Okay? With that in mind then, I'm going to start out at this point, and I'm going to say, according to this graph, at x equals 2, the slope was 0. That means it was kind of horizontal there. I'm just going to kind of put a little mini piece of a graph there just for a second. And then notice what was happening. As we go to the right, the slopes get bigger. Okay, now keep in mind that when slopes get bigger, what's that mean happens to your graph? That's right, you can read. It means it's steeper. Okay, so as we're going to the right, your graph is supposed to get steeper. Okay, so if I start here at fairly horizontal, and as I go toward this x value, my graph has to get steeper. Now, I don't know exactly how steep to make it. I know that it's supposed to get up to a slope of 1, so maybe something like that. And I'm just going to stop there. Okay, I can't keep going because these derivatives don't keep going. This graph of derivatives does not keep going. Okay. Now this whole section, these y values are getting bigger. So if these y values are getting bigger, then that means as I go toward the left, toward those x values, the graph should be getting steeper again. And again, the steepness of that little chunk of graph should be getting up to a slope of, well, this is a y value of 3, so it should get as steep as a slope of 3. Okay, now what you're not going to like is as these are going up, that means the slopes are, remember these slopes are positive because these y values are positive and these y values represent slope. All of these y values on this graph, all of these y values are slope. Okay, so that again means that as I'm going along here to these new x values, my slopes have to be positive. Okay, so here we go, fairly horizontal here. My slopes all the way until I get to this x value have to be getting steeper and steeper and steeper, and again it has to be a slope of about 3 when I get to here. Okay. All right, well we got one more section to go. I know this is not so much fun, and I'm sorry, but you got to see some examples of this. Okay, now these slopes, these y values on this graph are still positive, but they're decreasing, so that means it's getting less and less steep until it gets to this x value, wherever that is. And when that happens, this y value on this graph is 0, so that means the slopes are going to be 0 for that x value. All right, so here we go. That means I have to be getting less and less steep to there. And then ultimately, when I go here, these y values are negative, so that means the slopes for those x values will be negative also. So that means I have to be doing something like that. That's it. That's the graph. All right, the logic again is you're looking at the y values of this, the y values of the original graph here are slopes. So you have to kind of be translating back and forth in your head from, okay, that's a y value for derivative, so that means it's a slope. That's really about steepness. Okay, y value of derivative is about slope. Slope is about steepness. Okay, so again, if it's a positive y value for the derivative, in other words, a y prime value, it's got to be going up. If it's a negative y prime value, it's got to be going down. In other words, increasing, decreasing. Okay, got to move. We're in daylight. All right, we're going to go back to where we start out with the function, and then we'll graph its derivative. Okay, all right, so here we go. This is a piecewise function, which basically means you're going to graph pieces. So think of this as y equals 2x minus 1, y-intercept of -1, slope of 2. Looks something like this. Yeah, that's not too bad. It's supposed to hit right there and right there, so I'm off a little bit. Okay, and then the only catch is that that's really only supposed to be true for the x's. That's funny, remnants of a prior something or other. There we go. But I'm really only supposed to be graphing this for the x's to the left of -1. Well, -1 is there, so this bad boy has to go away. Okay, let me just make sure I have a little touch of an arrow there. Okay, and so it said less than, it did not say or equal to. There it is. So we are not including that point. y equals x squared looks something like this. And this is supposed to start at -1 and include it. That means the stuff to the left of it is gone. Okay, so this is f of x. Okay, so the green and blue graph is y equals f of x. It's a piecewise function, and that's it. Okay, so what we're going to try and do now is graph the derivative. Okay, so we're going to graph f prime. Okay, remember derivative is slope. Well, I love when we're talking about a line. So for these x values here, to the left of -1, those slopes are all the same. And what's awesome about it is those slopes are 2. So for all of the x values to the left of -1, I'm going to graph 2. Okay, a little bit of an issue here, okay, before we get too excited. That point that I just drew right here, is that accurate? Is that the derivative? What's going on here with derivative? What is the slope at exactly -1? Well, the slope on this side is 2. The slope on this side is actually -2. Now, just a little aside here, I'm going to go back to the rule you don't know. For y equals x squared, remember, and you can't really use this yet, on paper, but I'm going to go ahead and just throw it up here to remind you. 2 times 1, exponent times the coefficient, subtract 1 from the exponent. So that's 2x to the 1, also known as 2x. So if I do f prime of -1, that's going to be 2 times -1, you guessed it, -2. So that the slope of that guy is actually going to be -2. So the slope here is -2. So here's my question. Is this one filled in, or is that one filled in? Well, at -1, the slope can only be one thing. It can't be both -2 and +2, and the fact is, it's neither. So this is open, and this is open. Okay, now, these slopes are getting closer and closer to 0. So these numbers for the slope are getting closer and closer to 0. Something like that. These slopes are going up now. So as this gets steeper and steeper, the slopes of those points, as that thing gets steeper and steeper, whoop, hello, oh, there we go. The slope here is actually 2. The slope here is actually going to be 4. For the x value 1, the slope is 2. For the x value 2, the slope is 4. And yeah, that's actually a line, which should not be a shock, since there it is right there. Okay, so we just graphed the derivative. Now this red graph in its entirety is the derivative of this original function. We just did a picture of all of the slopes for this original function. Okay? Again, rewind as you need to. All right? I want to do one more thing, and then we'll be done with 3.1b. Sorry for the wait. All right, so I'm going to graph, this is f prime. I'm going to graph y equals 2. But I'm only supposed to be graphing it from -3 to -1. So here's -3, here's -1. So -3 is included, -1 is not. Okay, so everything else has to be erased. Okay, I'm going to fix my little open circle there. Okay? All right, so that's that part. Okay, I'm going to graph y equals -1. Okay, well, y equals -1 looks like this. But I'm only supposed to graph it from -1 to 5. Well, here's -1, the x value of -1, and here's the x value of 5. Now, those are both included. Okay, so we'll get rid of everything else. Okay? All right, so again, what did we just graph? We graphed the derivative. This is a graph of slopes. This is not f of x. This is a graph of slopes. Now we're supposed to graph the function, in other words, y equals f of x, that has that derivative. Okay, so what that means is, in this section of x values, from -3 to -1, I need to graph an equation that has the slope of 2. Now, just a reminder, I don't know what y value to start with. It doesn't tell me. Now, let's just pretend I told you that f of 2, I don't want f of 2, I want f of -2. I mean, it doesn't really matter. All right, let's try again. I'll just do f of 2, that's fine. So f of 2, let's say, is 1. Okay, so f of 2, the original function before a derivative, which we don't know, f of 2 is 1. So that means I have to start with this point. Okay, hopefully this will work, because I didn't think about this before. All of these slopes are -1. So that means all of the slopes that I'm going to draw from here, from -1 to +5, have to have a slope of -1. So I'm going to draw a bunch of points from that have that slope. All right, so here we go. Slope of -1, so I'm going down 1 over 1, down 1 over 1, down 1 over 1, up 1, left 1, until I get to this x value. Okay, I just don't want that dotted line staying there. Okay, cool. All right, so in other words, here it is. Okay, it stops here because that's all the information I have for this. Oh, no, that's interesting. Okay, now, supposedly, oh, there's a little issue with the problem. At -1, I can't have one slope on one side. Oh, well, no, can't do it. This had to be just less than, not less than or equal to. See how that works? You catch stuff in the middle. All right, so now I really don't even have to connect the next part of this to this function that I just drew, but I will connect it because I could say, you know, in the description it could say it was continuous. I didn't, but let's just add that in. So now I need a slope of 2. Well, the slope of 2, I can't go up this way because that's for the wrong x values. So what I'm going to do instead is I have to have a slope of 2 going this way, and I have to keep it going. Okay, and that's it. That's the whole function right there. This is f of x. So again, I just need another color. There we go. In this section, it has a slope of 2 because of that derivative. In this section, it has a slope of -1 because of that derivative. Okay, and that's it. All right, so okay, one more super quick example because I didn't plan on going this long, and sorry. This is estimating a derivative from a table. This was from this website. Thank you, this website. I appreciate your stuff being up there. And what we're supposed to do, you can read the problem, pause, read the problem. We're supposed to estimate the derivative for when t is 9. Okay, I just covered up the number, but that's the idea. Okay. All right. So remember, derivative is slope at a point. Okay. So basically, the idea here is if we had an actual equation, we could do this a little, you know, nicer, a little more sophisticated, in a more sophisticated way. But we don't. So all we can do is approximate. And so basically what's going to happen here, we want to approximate w of t. And the way we're going to do that is by doing slope. And there are 3 different options for this particular one. You could grab points around 9. I personally like this one the best of the 3 that I'm going to show you. And what you're going to do is basically find slope. So we're going to do y minus y over x minus x, and I'll let you subtract. You can do that. Okay, that's one approximation. Okay. Another approximation would be if I grab 9 and a point next to it. So I could do 16 minus 1532 over 12 minus 9, and you can find that slope. And then the third one is kind of obvious since it's similar to the last one. I could grab these two, 9 and the one next to it on the other side. Okay, so again, these are all approximations for derivative. Okay, so again, this would look like 1532 minus 1257 over 9 minus 6. And again, I'm going to let you subtract. Okay, please note, you can't start at this end and do a subtraction for that. That would be average rate of change. I want an approximation for instantaneous rate of change. Again, you need to go back and read the problem because what we're talking about is how fast is the wind's velocity changing. Okay, it's kind of like acceleration. Okay, and these numbers in this table are wind velocity at different times. Okay, one quick little note here. Again, I'm sorry for going long. There is a little picture here, illustration here, of if you use the 9 and the 12, that would be this one. If you use that one, the slope of this line would be what you're finding. Now, obviously, that's not a perfect estimate of derivative, but you know, when all you have is numbers, you don't have an equation. I mean, I don't know what equation fits this. This is kind of a jacked up mess. So I can't really do derivative in a symbolic way. Okay, so this is about 7 minutes longer than I wanted. I'm sorry for going so long. You know, and feel free to rewind all you need to, and talk to you in class.